last class we have studied what is Huygens principle. Huygens principle states that each point of the wavefront acts as secondary source of disturbance and the wavelets emanating from these points move with the velocity. Okay, velocity of the light in the medium, and if you draw common tangent to all the spheres, we will get the new position of wavefront, that is Huygens principle. So, importance of Huygens principle is it could explain reflection and refraction. First we can study how Huygens principle is used to explain reflection. Okay, so consider first a reflecting surface P dash. Here this is the reflecting surface, we can give the name P dash. P dash is the reflecting surface. Okay. Now consider two plane wavefronts AB and CD incident on the reflecting surface. So consider two plane wavefronts. These are the plane wavefronts AB and CD incident on the reflecting surface. Now first we can draw the two rays. Okay, we can draw two rays, and rays, we know the rays are mutually perpendicular to the wavefront. So we can draw two rays. So these are the two rays which are perpendicular to wavefront. Okay, so these are two rays which are mutually perpendicular to the wavefront. We can draw arrows. Okay, we can put arrows for the incident rays. So these two rays, these two represent incident rays, incident at the point A and C, and AB and CD represents incident wavefront. Okay children, so this is incident wavefront. AB also represents incident wavefront. Now we can draw a normal at the point A. At the point A we can draw a normal. So this is the normal, and we can mark the angle of incidence I. Clear? So here this is I means what is here, wavefront and the ray are mutually perpendicular to each other, isn't it? So here this represents I means what is this angle? This angle is 90 minus I, because both are perpendicular, no? So this represents I means the remaining angle is 90 minus I. Here normal and the surface are, reflecting surface are perpendicular. Now this angle 90 minus I means what is this angle? This angle is equal to I. Okay children. So here in the Huygens principle there is another definition for angle of incidence. Angle of incidence is the angle between incident wavefront and the reflecting surface. Okay, in ray optics we know angle of incidence means the angle between incident ray and the normal. And here in wave optics, using Huygens principle we can define angle of incidence as angle between incident wavefront and the surface. Okay. Now let V be the velocity of light in the medium. Here in the given medium, let V be the velocity of light. Let tau be the time taken by the wavefront to advance from B to C. See here this is the first wavefront and this is another wavefront. Let tau be the time taken by the wavefront to advance from B to C. Tau be the time taken from one wavefront to another. So what is the distance BC? The distance BC is equal to V tau, because velocity is equal to distance by time, isn't it? Velocity is equal to distance by time. So what is the distance? Velocity into time. Here distance BC equal to velocity into what is the time from one region to another, tau. So the distance BC is equal to V tau. Clear? Now taking this V tau as radius, we can draw a sphere from the point A onto the same reflecting surface. Okay. So in order to construct the reflected wavefront, we draw a sphere of radius V tau from the point A. So here this is Huygens principle is based on the geometric construction, pure geometric construction. So taking this V tau as radius, we can draw a sphere from the point A like this. So here keeping V tau as radius, draw a sphere from the point A. So here I have drawn only a curve, you can draw a sphere also, a complete sphere. So here let this is the arc drawn with radius what? V tau from the radius A. This is the arc. So see the note. In order to construct the reflected wavefront, we draw a sphere of radius V tau from the point A. Now draw a tangent from C to the sphere or to the curve. Draw a tangent from C to the curve like this. Now we can draw a tangent from C onto the curve. Let the point be E. Now this EC is called reflected wavefront. So draw a sphere from the point A with radius V2 and then draw a tangent from C to the curve or to the sphere. Let it meet at the point E. Now EC is called reflected wavefront. So here EC is called reflected wavefront. Now draw a perpendicular from A to the reflected wavefront. We know any line drawn perpendicular to the wavefront is called a ray. So here also draw a perpendicular from A to the reflected wavefront like this. So this AE is called a reflected ray. So this represents a reflected ray. Okay. So here EC is called a reflected wavefront and AE is called a reflected ray. So A is drawn perpendicular to the wavefront and hence it is called a reflected ray, and we can mark this angle. This is the normal. So this angle is angle of reflection R. Okay. So once more I will explain the step. First PP dash represents the reflecting surface, AB and CD represents the incident wavefront. Now draw rays at the point A and C. So these red line with the arrow represent the incident rays. So this represent the incident ray. Here this is called the incident ray. So draw incident rays at the point A and C. Okay. Now we can say tau be the time between the two wavefront to advance from one point to another point of the wavefront. V be the velocity of light in the medium. So what is the distance from one wavefront to another? Let it be V2. Taking this V2 as radius, draw a sphere from the point A like this. Now draw a tangent from C onto the sphere or onto the curve. It meets at the point E. So what is this EC called? That is called the reflected wavefront. Now draw a tangent to the reflected wavefront, that is AE, which is called a reflected ray, and hence this represents the angle of reflection. Okay. So in order to construct the reflected wavefront, we draw a sphere of radius V tau from the point A. Let CE represents a tangent drawn from C onto the sphere. CE represents a tangent. Draw a perpendicular from A to CE, where CE is called a reflected wavefront, which gives the reflected ray. So draw a perpendicular from A onto CE, which gives the reflected ray. Now we know that there are two laws of reflection. Incident ray, reflected ray and normal all lie in the same plane. So here we can say incident ray, reflected ray and normal all lie in the same plane. So using this figure we can explain the first law of reflection. What is the second law of reflection? Angle of incidence and angle of reflection are equal. So that we have to prove. Okay, so how will you prove an angle of incidence and angle of reflection are equal? For that, consider triangle AEC, this one AEC, and triangle ABC. Now consider triangle AEC and triangle ABC. Triangle AEC and triangle ABC. Here angle E, angle B, both represent 90 degree, no? So this is the reflected wavefront, this is the ray, both are perpendicular. This is the incident wavefront and this is the ray, again both are perpendicular. So these two angles represents 90 degree, that is 90 degree. And for both the triangles AC is common, AEC and triangle ABC, AC is common. So angle A equal to 90 degree, angle B equal to 90 degree, AC common. Okay. Now what is the distance BC? BC is equal to that angle, the distance BC equal to V2. And for the triangle AEC also AE equal to V2, because we had drawn the sphere with the same radius V2, isn't it? So AE equal to V2, similarly BC equal to V2. Hence we can say that the two triangles are congruent. Triangle AEC and triangle ABC are congruent triangles, and hence the angle I and R are equal. Okay, since the two triangles AEC and triangle ABC are congruent, angle of I and angle R are equal. This is angle R. because angle between incident wavefront and the surface is angle I, angle of incidence I. Similarly, the angle between reflected wavefront and the surface is also angle of reflection R. Okay children, angle between incident wavefront and the surface is I. Similarly, angle between reflected wavefront and the surface is also R. So, I and R are equal. So, hence we could prove, Huygens principle could prove which one? Laws of reflection. Thus, Huygens principle could satisfactorily explain the laws of reflection. Okay children. Now, we can see how Huygens principle is used to explain refraction. Explanation of refraction using Huygens principle. Let P dash is the interface which separates two transparent media 1 and 2 having velocities of light v1 and v2, refractive index n1 and n2. Okay, so this is the interface which separates two transparent medium. This is the first medium which is the rarer, and this is the second medium, this is the denser medium. First we can discuss what happens when a ray of light travels from rarer to denser. Okay, so consider the interface P dash which separates two transparent media. Number one is rarer and second medium is denser. Consider two plane wavefronts AB and CD incident on the interface. So, AB and CD are the two rays which are incident on the interface. Okay, interface which separates the two transparent media. So, AB and CD are incident wavefront. Okay, AB and CD represent two incident wavefronts incident on the interface. Now, we can draw two rays which are perpendicular to the wavefront. So, these are the two rays. We can draw two rays at the point A and C. So, these are the two rays drawn at the point A and C. Now, we can draw a normal at the point A. Here this is the normal, and we can mark the angle of incidence. This is the angle between incident ray and the normal. This represents the incident ray. Angle of incidence. Now, that we know that angle between normal and incident ray is angle of incidence. Angle between incident wavefront and surface is also angle of incidence. Okay, so this is also I. Now, let tau be the time between or time taken by the wavefront to advance from one wavefront to another. Here we can take the notes. So, let tau be the time taken by the wavefront to travel the distance BC. Okay. Let BC, this is distance BC, tau be the time taken by the wavefront to advance from one wavefront to another. Here the velocity of light in the first medium, let it be V1. V1 be the velocity of light in the first medium. Here velocity of light in the second medium, let it be V2. Okay. So, here the velocity of light in the first medium is V1, and what is the time taken by the wavefront to move from B to C? Tau. So, what is the distance BC? BC is equal to velocity into time, therefore, it is V1 tau, because V1 is the velocity, tau be the time taken by the wavefront to move from one point to another. Okay, so, this distance BC is equal to V1 tau. Now, so BC is equal to V1 tau. In order to determine the shape of the refracted wavefront, we consider a sphere of radius V2 tau from the point A in the second medium. Okay. So, here let the distance between two incident wavefront be V1 tau. So, what is the distance between two refracted wavefront? That will be V2 tau, because here the velocity in the second medium is V2. Okay, so the distance between two refracted wavefront will be V2 tau. So, taking that V2 tau as a radius, we can draw a sphere from the point A on the second medium, which is the denser medium. Clear children? So, V1 tau is the distance between two incident wavefront. So, distance between two refracted wavefront will be V2 tau, and taking that V2 tau as radius, we can draw a sphere from the point A. And V1 is the velocity of light in the rarer medium, and V2 is the velocity of light in the denser medium. We know that velocity in the rarer medium is always greater than velocity in the denser medium. Okay. When a ray of light is traveling from rarer to denser medium, what happens to its velocity? Velocity decreases. Velocity is greater in the rarer medium, that you know. So, here V2 tau is always, what is V2 tau? V2 tau is lesser, because rarer to denser means velocity decreases, isn't it? So, V2 tau is always less than V1 tau. Clear children? So taking that V2 toe as radius, we can draw a sphere from the point A like this. Here this is the sphere. I have drawn only the curve. You can draw a curve or a sphere. Okay, full sphere you can draw. So what is the radius of that sphere? V2 toe. V2 toe is lesser, isn't it? So taking that V2 toe as radius, draw a sphere from the point A or draw a curve from the point A. Clear children? So here, in order to determine the shape of the refracted wavefront, we draw a sphere of radius V2 toe from point A in the second medium. Now we can draw a tangent from C onto the sphere or onto the curve like this. Draw a tangent from C onto the curve. So draw a tangent from C onto the curve. Let the point be E. Okay, so EC is called, what is this EC called? This is called refracted wavefront. So CE represents refracted wavefront. So let C is the tangent drawn from C onto the sphere. C is called refracted wavefront. Now draw a perpendicular from A onto the refracted wavefront. Draw a perpendicular from A to the refracted wavefront. Any line which is perpendicular to the wavefront is called a ray. So draw a ray from point A to this wavefront. Let it passes through the point E like this. So consider a perpendicular drawn from A to the refracted wavefront. Draw a perpendicular from A to the refracted wavefront, which is ZE, and which gives the refracted ray. So this gives, what is this called? AE is called a refracted ray, and this angle is called the angle of refraction. So from the figure itself, it is clear that when a ray of light is travelling from rarer to denser, it bends towards the normal, isn't it? When a ray of light is travelling from rarer to denser medium, it bends towards the normal. Since this is R, here this angle will be angle of refraction R. Okay children, so angle of refraction can be defined as the angle between refracted ray and the normal, or angle between a refracted wavefront and the surface. Clear? Now, how Huygens principle is used to explain refraction? So we know two laws of refraction. The first law is incident ray, refracted ray and the normal lie at the same plane, lie on the same plane. So incident ray, refracted ray and the normal all lie in the same plane. So that law is satisfied. Second law is, we can prove the second law from this figure. Consider the triangle ABC. If you take the triangle ABC, this is 90 degree. Okay, take sin I. What is sin I? Sin I equal to opposite side divided by hypotenuse. This is 90 degree, no? So AC represents the hypotenuse. So sin I equal to BC divided by AC. And what is the value of BC? BC is equal to V1 toe. So V1 toe divided by AC. Clear children? Similarly, we can take another triangle AEC. This one. Triangle AEC. This is also 90 degree. Triangle AEC. Again take sin R. What is sin R? Sin R equal to AE, opposite side divided by hypotenuse. AE divided by AC. AE divided by AC. What is the value of AE? A equal to V2 toe. Because taking V2 toe as radius, we had drawn the sphere, no? So the distance AE equal to V2 toe divided by AC. Clear children? So sin I equal to V1 toe divided by AC. Sin R equal to V2 toe divided by AC. Now we can take sin I by sin R. Sin I by sin R equal to, we can divide these two, V1 toe divided by AC, the whole divided by V2 toe divided by AC. AC and AC get cancelled. Toe and toe get cancelled. So it becomes V1 divided by V2. So sin I divided by sin R equal to V1 divided by V2. We know The refractive index of any medium is given by n equal to c divided by v. Absolute refractive index of the medium is n equal to c by v, where c is the velocity of light in vacuum, v represents the velocity of light in the medium, that you know, n equal to c by v. So, v1 can be written as, using this formula, v1 can be written as c divided by n1, isn't it? So, v1 equal to c divided by n1 divided by v2 equal to c by n2. Clear, children? C and c get cancelled, it becomes n2 by n1. So, we got the formula sin I divided by sin r equal to v1 divided by v2 equal to n2 divided by n1. And what is this law called? This is called Snell's law. Snell's law of refraction. Hence, Huygens principle, or from the Huygens geometric construction, we can derive this Snell's law. Hence, we can say that Huygens principle could explain a refraction of light. Okay, so first take the two triangle ABC and triangle AEC. Take sin I and sin R, just divide the two, we will get sin I by sin R equal to V1 by V2 equal to N2 by N1, and the law is called Snell's law, and hence we can say that Huygens principle could explain refraction of light. Now we can see what happens when a ray of light is travelling from denser medium to rarer medium. Let the first medium is denser and the second medium is rarer. Okay, here also we can consider two incident wavefronts. Here it is AB and CD. AB and CD are the two incident wavefronts, and we can draw rays at the point A and C. So, these two represent the incident rays. So, this is incident wavefront. We can draw a normal at the point. Again, we can draw the angle of incidence, mark the angle of incidence. Okay. Here, let the BC, the distance BC is equal to V1 tau. We know tau be the time taken by the wavefront to advance from one point to another. So, the distance BC is equal to V1 tau. V1 is the velocity of light in the denser medium. Okay, so this distance is V1 tau. Now, the distance between two refracted wavefront. What is the distance between two refracted wavefront? That will be V2 tau, because the distance between two incident wavefront is V1 tau. So, the distance between two refracted wavefront will be V2 tau. What about V2 tau? V2 is greater because denser to rarer, velocity increases, no? So, V2 is always greater than V1. Rarer medium velocity is greater, isn't it? So, V2 tau is greater than V1 tau. So, taking that V2 tau as radius, we can draw a sphere from the point A like this. So, here this is a sphere of radius V2 tau. V2 tau is greater. So, this is a bigger sphere, okay, of radius V2 tau. Draw from the point A. Now, as before, draw a tangent from C onto the sphere. Draw a tangent from C onto the sphere like this. Let the point be E. Okay, EC represents a tangent from C onto the sphere. Now, draw a perpendicular from A to this wavefront. So, actually EC represents the refracted wavefront. Okay, so taking V2 as radius, we have drawn the sphere and that sphere is greater. Then draw a tangent from C onto the sphere. Let that point be E, and EC is called a refracted wavefront. Now, draw a perpendicular from A onto the refracted wavefront, and what is that called? This is called a refracted ray. Mark the arrow. This is called a refracted ray. So, we know that here this angle is angle of refraction R, because this is the refracted ray, this is the normal. Here from the figure itself, it is clear that when a ray of light is travelling from denser to rarer, it bends away from the normal. Okay, so denser to rarer, the ray of light bends away from the normal. Clear, children? So, here also we can prove incident ray, refracted ray and the normal all lie in the same plane. Then here also we can prove sin I by sin r equal to n2 by n1. Sin I divided by sin r equal to n2 divided by n1. Okay children, so this is the explanation of Huygens principle when a ray of light is travelling from denser medium to rarer medium. First you draw two wavefronts, then you draw two rays, mark the angle of incidence. Let V12 be the distance between two incident wavefronts. So distance between two refracted wavefront will be V22, which is greater, isn't it? V2 is greater. Now draw a sphere from the point A onto the second medium with radius V22. Then draw a tangent from C onto the sphere, that is called a refracted wavefront. Now draw a perpendicular from A to the refracted wavefront, which is a refracted ray. Okay.